Good morning, students. Today we will discuss the chemical properties of aryl halides. We will classify the chemical properties of haloarenes or aryl halides into four categories. The first one is nucleophilic substitution reaction. The second one is reaction of aryl halides with metals. Third one, electrophilic substitution reaction. Electrophilic substitution reaction. And the fourth one is reduction of aryl halides. Now let us start with the first reaction of aryl halides, that is nucleophilic substitution reaction. We have studied about nucleophilic substitution reaction in alkyl halides also. Now for aryl halides, let us take the example of chlorobenzene. Now when chlorobenzene will be substituted by a nucleophile, let the nucleophile be Nu. So for nucleophilic substitution, this Cl minus should be replaced by Nu. For that, the CCl bond should be broken. So, suppose if in case of a compound, this carbon halogen bond is difficult to break, or if the cleavage of the bond is difficult, then the nucleophilic substitution reaction will not take place easily. That means a nucleophilic substitution reaction will be difficult. Now we will apply this in case of nucleophilic substitution of haloarenes, and let us see the results. Now say this, haloarenes or aryl halides are chemically less reactive than haloalkanes towards nucleophilic substitution reaction. That means if we compare the reactivity rate of chlorobenzene and methyl chloride, then it is the methyl chloride which will undergo nucleophilic substitution reaction faster than that of chlorobenzene. For example, if I take chlorobenzene and methyl chloride and treat both of this with alcoholic solution of silver nitrate, and then I am heating it. So what I am doing? I am heating both this chlorobenzene and methyl chloride with alcoholic solution of silver nitrate. Now in case of methyl chloride, we will obtain a cardi white precipitate after some time. But chlorobenzene will not at all give this cardi white precipitate with silver nitrate solution. So we can say that the rate of reaction towards nucleophilic substitution is much faster in case of methyl chloride when compared to chlorobenzene. That means, in a simple language, we can say that haloarenes are not susceptible to nucleophilic substitution reaction. Let us see the reason. The low reactivity of haloarenes or aryl halides towards nucleophilic substitution reaction can be explained with the help of two factors. What are the two factors? The first factor is resonance and the second factor is hybridization. Let us start with the first factor, that is resonance. Now, chlorobenzene will have a number of resonating structures. Let us draw the resonating structure of chlorobenzene. We know that Cl will have how many lone pairs here? 3 lone pairs. Now, for showing the resonating structures, at present I have drawn here only one lone pair. But here you have another lone pair, here another lone pair. Now this will come here and this bond will be broken. So the next structure will be, here there will be a double bond and Cl is plus. Here you have negative charge, this bond intact. Here also this bond. Now next step, what happened? Here it will make a bond and this bond will be broken. All of you draw the resonating structures with me. Cl plus, here again double bond, this double bond intact and here negative charge. Now in the next step, what will happen? This will come here. So this is intact. Here bond making, here negative charge and here double bond Cl plus. In the next step, this and the electron pair will go to its own place. So here this one, this. Now in the structures you will see that CCl bond in chlorobenzene has acquired partial double bond character. Why? Due to which phenomenon? Due to resonance. See here, CCl, CCl, here also CCl. It has attained what? Partial double bond character. Now we know that double bond is shorter than single bond. So this development of partial double bond character means shortening of carbon halogen bond. If the bond shortens, that means the bond will become more stable, more amount of energy will be required to break it. That means this CCl bond becomes more stable. If this bond is more stable, then cleavage of carbon-halogen bond becomes difficult. Now, if the cleavage of this CCl bond is difficult, then nucleophilic substitution will also become very difficult, because in nucleophilic substitution reaction, you need to depart this Cl with this electron pair. That means Cl should be departed with Cl minus. For this CCl bond should be broken. But due to resonance, what is happening? Due to resonance, this CCl bond is acquiring partial double bond character. That means shortening of CCl bond is taking place, and this imparts stability to the molecule. Now, if this bond, CCl bond, is becoming stable, then cleavage of this bond is very difficult. And if this CCl bond cleavage is difficult, then nucleophilic substitution reaction will be very difficult. So, this is one of the factors for the low reactivity of haloarenes towards nucleophilic substitution reaction. Now, the slow reactivity of haloarenes or aryl halides can also be explained with the help of hybridization concept. Before we discuss this concept, let us first clear this concept. This is carbon-halogen bond. Now, if this carbon-halogen bond is broken easily or cleaved easily, then the rate of nucleophilic substitution reaction will be faster. Now, suppose if carbon holds this shared pair of electron towards itself strongly, will the CCl bond break easily? No. Carbon-halogen bond, in this case, if carbon is having this effect, that means if carbon is holding this shared pair of electron towards itself, then Cl will not be able to depart as Cl minus easily. And this departure of Cl or the departure of X as X minus is an essential requirement for nucleophilic substitution reaction. Now we will see the state of hybridization of this carbon, that means the carbon attached to the halogen in haloarenes. Now this carbon is having how many sigma bonds? 1 sigma, 2 sigma and 3 sigma. So the state of hybridization of this carbon in chlorobenzene is sp2. Now let us draw this alkyl halide. Here how many sigma bond? 1 sigma, 2 sigma, 3 sigma, 4 sigma. So the state of hybridization of carbon here is sp3. 3 sigma bond, so sp2. Here 4 sigma bond, so sp3. So S and 3p4. Now let us see that how this state of hybridization is bringing a change in the rate of nucleophilic substitution reaction. So here carbon is sp2 and here the carbon is sp3. Now we know that CsP2 carbon is more electronegative than CsP3 carbon, because in CsP2 carbon the S character is more. More the S character, electronegativity. In sp2 carbon, the S character is 33.3%, whereas in sp3 carbon, the S character is how much? It is 25%. And in sp carbon, the S character is 50%. So, sp carbon is the most electronegative. Now, if we compare CsP2 carbon and CsP3 carbon, CsP2 carbon is more electronegative than CsP3 carbon. Now, if CsP2 carbon is more electronegative, then what will happen? This carbon will hold this electron pair tightly. So, it will hold the shared electron pair tightly. So if this holds this shared electron pair tightly, then cleavage of this bond will be difficult. So cleavage of which bond? CCl bond. That is carbon-halogen bond will be difficult. If the cleavage of CCl bond is difficult in case of chlorobenzene, then rate of nucleophilic substitution will be obviously slower than that of alkyl halide. So, the rate of nucleophilic substitution of aryl halides is much slower than that of alkyl halides. That means at normal conditions, aryl halides will not undergo nucleophilic substitution reaction. But at drastic conditions or extreme conditions, nucleophilic substitution reaction can take place in case of aryl halides. And this can be explained. That means if you were asked that why aryl halides undergo slow nucleophilic substitution rate than that of alkyl halides, you will explain this with respect to two factors. What are those two factors? Resonance concept and hybridization concept. Now we will discuss the nucleophilic substitution reactions of chlorobenzene. Under ordinary conditions or under normal conditions, chlorobenzene will not undergo nucleophilic substitution. But under extreme conditions or drastic conditions, chlorobenzene will undergo nucleophilic substitution reaction. First, let us discuss the substitution of the halogen atom of chlorobenzene or halobenzene or aryl halides by hydroxy group. That means here we will convert chlorobenzene to phenol. So how we will carry out this? Now first we will heat chlorobenzene with aqueous NaOH solution. Now at ordinary temperature the reaction will not take place. So the temperature should be 623 Kelvin and high pressure of 300 atmosphere. Now initially sodium phenoxide will be formed, which on acidification with dilute acid gives us phenol. So, chlorobenzene to sodium phenoxide. So, here you see I have written 2 NaOH. So, NaOH, NaOH. OH. So here H2O. Now this Na, so H2O, so I am writing here minus H2O. Now see this Na and this Cl. So minus NaCl. So what is left behind? This Cl is replaced first by ONa. So here I have written ONA. So chlorobenzene plus 2NaOH, when this is heated at a temperature of 623 Kelvin, the pressure is 300 atmosphere. So initially we will get this, which on acidification will give us phenol. Now if you were asked convert this chlorobenzene to phenol, so how you will write the conversion? Here you will write NaOH aqueous, then 623 Kelvin heat, and number 3 you will write 300 atmosphere pressure. Now this reaction is a very important reaction. This is the manufacture or industrial preparation of phenol, and this process is referred to as Dow's process or Dow's method of manufacture of phenol. You will write this one just for understanding. This you don't have to write in the equation. So now our second substitution will be substitution by NH2 group. That means we will convert chlorobenzene to aniline. First we will write the balanced equation. Two chlorobenzene when heated with aqueous ammonia in the presence of Cu2O at a temperature of 475 Kelvin and pressure 60 atmosphere, we will get aniline plus Cu2Cl2 plus H2O. First write this equation. 2 aniline plus 2 ammonia aqueous, Cu2O cuprous oxide, temperature 475 Kelvin, 60 atmosphere. You will get 2 moles of aniline plus Cu2Cl2 plus water. If you are asked convert, then what you will write here? Simply you will write ammonia aqueous in the presence of Cu2O 475 Kelvin, 60 atmosphere. This is the balanced equation and this is the conversion. Written this? So now we will discuss the next substitution, that is substitution by cyano group. So substitution by cyano group. So here again the conversion will be chlorobenzene to cyanobenzene. Now when you will heat chlorobenzene with CuCN at a temperature of 475 Kelvin in the presence of pyridine, you will get cyanobenzene plus CuCl. So chlorobenzene plus CuCN, 475 Kelvin, pyridine, you will get cyanobenzene plus CuCl. So conversion, what you will write? You will write CuCN 475 Kelvin and pyridine. You have to heat this. Now this is all about the nucleophilic substitution reactions of aryl halides. So today we have discussed the nucleophilic substitution reactions of aryl halides. And we have seen that these aryl halides will not undergo nucleophilic substitution reactions under ordinary conditions. We have also explained the reluctance of these aryl halides towards nucleophilic substitution reaction with the help of two concepts. What are these concepts? Resonance and hybridization. So we have also discussed the three substitution reactions of chlorobenzene under drastic or extreme conditions. We have learned the conversion of chlorobenzene to phenol by Dow's process. Then we have learned the conversion of chlorobenzene to aniline and cyanobenzene respectively. In our next class, we will learn the reactions of aryl halides with metals and electrophilic substitution reactions of aryl halides. So, this much for today. Thank you very much. Have a nice day.